Hello, mathematicians, puzzlers, and other curious people. I'm Avrila at Math with Avrila. Welcome to our Whiteboard Wednesday party. Now, this is going to go on for a while, so I may be in and out of the room a couple of times. I will leave puzzles up anytime I need to step out of the room. And I want to start uh, with putting a puzzle on the board. So this is a set of equations from an alternate number universe. So one of them is that 2 plus 3 equals 5. Well, that doesn't seem very alternate. How's that an alternate number universe? Let's see. Also, 1 plus 3 equals 4. Okay, well, that seems fairly usual. Well, now on the other hand, though, here's one that's going to seem more alternate. 5 plus 4 equals 2. This should be making everybody go, huh? But remember, it's an alternate number universe. Now, it's actually an alternate number universe you're very familiar with. Yes, you've met this alternate number universe before, but I've never studied alternate number universes, some of you might be saying. Okay, now, I know some of you might have some extra knowledge also. I'm going to skip over you all for a little bit because, spoilers. So let's see, 5 plus 4 is 2. Well, that's really weird. And we can multiply in this alternate number universe. So like 4 times 1 is still 4. And 2 times 3 is still 6. But 3 times 3 is 2. Let's see. 4 times 3 is 5. Okay, so it still goes up by 3s, but it's so weird. So what kind of alternate number universe is this? Well, we can analyze it a little more closely by organizing what we're observing here. So we can make an addition table of everything we've seen so far. So we've seen 1s, 2s, 3s, 4s, and 5s. And we know that 6 also is part of this alternate number universe. Okay, so you can handle this either way, but I'm going to say that these will be the first number in case that matters, because there are some alternate number universes where the order matters. So we're going to say, okay, 2 and 3 is 5. 1 and 3 is 4. Okay. 5 and 4 is 2. Weird. Okay. Now we can do the same thing with multiplication. So again, so far we've seen that there is such a thing as 1, 2, 3, 4, 5, and 6 in this alternate number universe. And again, this direction will be the first of the two numbers. So we've got that 4 times 1 is 4. 2 times 3 is 6. 3 times 3 is 2. That's bothersome. And 4 times 3 is 5. Okay, so I'm going to leave that sitting there. I'll add some more clues on in a little while. The next thing I had in mind, and I will need to pull some notes back up for this because I had to reboot my computer and the notes got lost. But the next thing I had in mind is A puzzle called The Game of 24. Now let's see if I can find it. Where'd it go? Well, let's see. Okay, well, let's just get another one generated then. So what we are trying to do here is make 24 out of 4 numbers. So the 4 numbers we have available are 12, 2, 13, and 11. And we can use those numbers however we want. So these are randomly generated at 4nums.com. That's 4nums.com. So let's look at these and see how we can get 24. Well, we could get 24 by doing just 12 times 2. But there's a problem with that, of course. Yeah, I'm sure you see it. We still have to use the 13 and the 11. So one thing that can be useful for playing this game is making a list of possible factor pairs for 24, because one way we could get 24 is by multiplying. So we could do 1 and 24, or 2 and 12. I see we could get a 2 by doing 13 minus 11, but then we'd still need to figure out something to do with the 12 and the 2. Let's see, 3 times 8, or 4 times 6. 5 doesn't work, and then we're in repeats. Let's see what we can do here. So it seems to me we can get 24 twice pretty easily here, because 13 plus 11 would be 24. And 12 times 2 would be 24. The challenge is going to be getting them all in something that runs up to 24. So we could try making an addition table out of the numbers we have, and then a subtraction table, a multiplication table, a division table, and see what we can come up with. So let's take a look. So we've got 2, 11, 12, and 13. So this will be our addition table, but we'll make them with other operations also. And we can't use the same number twice. And we really only need to fill out the upper part because addition is commutative. So we can get 13, 14, 15 easily. Whoops. 13 another way. 14 another way. Whoops. Oh, wait. Not 13 and 14, 23 and 24. Wow. Okay. Need more caffeine. No worries, though. We'll get through. 23, 24, or 25. Now, if we have some way that we can go up and come back, that might be okay that we've got a 25 there. I'm not seeing it yet, but it might be something we use. There's no rule that we have to stay below 24 the whole time. Okay, so now I'm going to make one for multiplication to see what we've got. And because I'm already using the x, I'm going to use the dot. So let's see, I can get 22, 24, or 26. Let's see, 11, 12 would be 132. 11 and 13 would be 143. By the way, do you all know the trick for doing 11s very quickly? So like that 13 I did, well, 10 13s would be 130. One more 13 added on would be 143. So when you have a 2-digit number that you're looking to multiply by 11, you can just say, okay, split the number and then add its digits together in between and get 143. Now, that gets trickier when the digits are less compatible, such as if we had 67 times 11 that we wanted to do, because then we'd say, okay, well, now we have to carry, and it's just less tidy. Okay, let's see, 12, 13, well, 144, and 12 more would be 156. Now, I'm just guessing that most of those are not going to be useful. I don't know for sure, but it seems like some of those numbers are big enough to be difficult to come back down from and stay in integers. We might also use subtraction, though. Okay, now this time the order does matter because it's possible we could go into negatives and then come back up. So again, I'm going to say that this one is the first. So 11 minus 2 would be 9. 12 minus 2 would be 10. 13 minus 2 would be 11. 12 minus 11 would be 1. Interesting. 12, 11. Can I do anything with 2? And 13. I don't see it. Okay. Maybe we'll circle back to that. 13 minus 11 would be 2. And then 13 minus 12 would be 1. Okay. And then on the other hand, 2 minus 11 would be negative 9. 2 minus 12 would be negative 10. And we can just basically copy these over, flipping the sign. And that's a property that often gets used in solving some problems, that if you have A minus B, well, you can flip their order, but it comes out to their opposite because of how signed numbers work. Okay, now division. Now we want this to be the whole number 24, not some weird decimal. So I'm guessing that we can eliminate options that are not neatly divisible, since I don't see any way to kind of come back from that by remultiplying it by the same thing. Okay, so I know I don't want to go into crazy decimals. At least I suspect I don't want to go into crazy decimals. So I'm going to not figure out this upper part where we're doing things like, oh wait, my bad, that would be the one we would do. Okay, well, let's see, 11 divided by 2, well, that's a decimal. 12 divided by 2, well, that's 6. 13 divided by 2, decimal, 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 decimal. So the only thing we can get by division is that 12 divided by 2 is 6. And I don't see a way to use that. Okay, so now let's look again at ways we can get some different numbers. So let's see, if I just gotta work this through. If I did 12 divided by 2 and got 6, I would need a 4 to multiply by it, or an 18 to add on, and I don't have any of that. Let's see what I can get, though. This is definitely a tricky one. I wonder if any of these bigger numbers are multiples of 24. I don't think they are, but I'm going to check to make sure. So I'm going to grab my calculator. Yeah, it's the one on my phone. Nothing fancy. I'm just doing basic operations. And I'm going to say, okay, 132 divided by 24. Yeah, that's a decimal. And 143 divided by 24. That's not going to work, I'm sure, but let's just make sure. Okay, that's a crazy long decimal. And 156 divided by 24. Okay. So yeah, those aren't going to happen. Let's see, what can we do? Okay, so I was thinking as I was writing these that subtracting something and getting a 1 and then multiplying it could be useful. So either 12 and 11 or 13 and 12. So either way, I have to use the 12 in that. So let's see. 13 minus 12 would still leave the 2 and the 1. Yeah, so that's not going to happen. There's got to be something in there. Do any of you have some hints for me? I'll take feedback. Let's see. I'm still kind of curious about this 26. That seems close enough to come back from. So if we did 13 times 2, that would give us 26. What I really want is a minus 2 to get 24. And I would have 12 and 11 to get it. Let's see, I can get minus 1. I don't see how to get a 2 out of that. It's a tough puzzle. Why did this program give us such a tough one for the first time we clicked on it? Well, it's randomly generated, so it doesn't really decide things like that. I remember I was getting that some of these were some crazy decimal multiple of 24, so I'm going to try out getting these decimals after all. Maybe I could divide by some of them and then come back. So let's see, 11 divided by 2 would be 5.5. 13 divided by 2 would be 6.5. 12 divided by 11 would be 1 point something. I'm really more interested in these, so I'm going to come back up and check these. So let's see. 12. Okay, so 132 divided by 24. Well, that was 5.5 times 11. Oh, sorry, 5.5 times 24. So if I could do 132 divided by 5.5, that would give me 24. I can get 5.5 by using 11 divided by 2. And then the 132, unfortunately, would have to be 12 times 11. So I'm having to use the 11 twice to get that. Okay, so that one doesn't work. Let's try the 143. Okay, that's 5.95 blah, blah, blah times 24. I don't think that one's helpful. And then 12 times 13. Let's take a look. So 156 divided by 24. So that's 6.5 times 24. So if we could get 156 divided by 6.5, but we're running into the same problem. We need the 13 twice for that to work. Oh, hey, what's up?
I have macaroni and cheese.
Ah, the mathematical macaroni. Did you come up with how this is mathematical?
I boiled it for 8 minutes.
Okay. And what was that based on?
How long it takes for the pasta to turn into
Okay.
soft.
All right then.
Stuff.
Let's see. I noticed that it's shell-style pasta, so topologically, it's basically a circle. Let's see. What else can we see about this? We could measure the volume by seeing how much sauce it took to fill it up. What else could we do with this macaroni?
Eat it?
I mean, mathematically.
Oh, I'll leave you to that. I'm not a cook.
Okay, well, the temperature of this macaroni is a decreasing function until it assumes room temperature. So I'm going to take a moment with this macaroni and eat it while it's good. So feel free to stare at either of these puzzles, and I'll be back with you in a moment. And I'm back. And by the way, the macaroni was awesome. I don't know why, if it's if it's a topological thing or what, but the shells that are topologically equivalent to a circle just always seem so much fancier than the tubes that are topologically equivalent to a torus. Not torus like a car, torus like a donut. Okay, so I want to do a couple more things in our alternate number universe. So if you've got a preference as to which one I do, feel free to put it in the comments right now. Okay, so no one's shouting out a preference, so I guess I'll pick. So we've got the 2 plus 3 equals 5. It turns out that 3 plus 2 also equals 5. So that's good. It seems like maybe the usual symmetry works. Let's see. How about 6 plus 6? I know you would usually say 12, right? But 12 isn't part of this universe. So 6 and 6 make, let me figure this out, 5. And I know, now you're saying, what? No, 6 is more than 5 already, and then there are 2 6s. Yeah, but it's an alternate universe. Things don't all work the usual way. Let's do a couple of multiplications also. We did 6 plus 6. Let's do 6 times 2. And it turns out that 6 times 2 is also 5 in this universe. Okay, so multiplication works the usual way. It's adding that many of the things. So we could say, okay, also, well, we didn't add anything else to itself, but where we multiplied something by 2. Okay, so 2 times 3 would be 6. Okay, well, that means 3 and 3 would be 6. Okay, so this part through here still kind of looks like a normal addition table. Oh, and I just realized I put that out of place. 6 times 2, so that would be there. Yeah, but let's go ahead and do 6 times 6. So 6 times 6, well, that would usually be 36. But in this alternate number universe, it's 1. What? Why? How? This is weird. Okay. So this alternate number universe also has, well, it also has a 0, but we haven't quite got that far yet. So I'm just going to do one more. So I'm going to say that 3 plus 4 equals 7. But I'm going to put a little mark on that because that's something we're going to have to come back to later. So this might give you a clue about that number being significant in this alternate number universe. Okay, so let's come back to this 24 puzzle. So we're trying to make the number 24 by using the numbers 12, 2, 13, and 11. And we've been having some trouble with it because it's not an easy combination of numbers. So let's see what we can figure out. So adding the 13 and 11 together would work. Multiplying the 12 and 2 would work. But getting everything used up seems a bit trickier. I'll be honest, I'm just about stumped on this one. I don't want to just Google it and cheat, but I'm a little low on ideas. So let's try making a systematic list of what we've got and see if that helps. So let's take a look. Okay, so we can rearrange these as much as we want to. Hey. Hey, what's up?
I need light.
Ah,
Light.
Light is important.
It is.
Yeah. Okay, so the 12 could go with the 2, or with the 13, or with the 11. Let's try putting the 12 with the 2. And we can do that different ways. Okay, so that gives us something to start with. We could also consider the 12 and the 13. So 12 and 13 would be 25. We could do 13 minus 12 and get 1. Let's see, we could do 12 minus 11 and get 1. Oh, whoops. I'm stuck on an operation instead of a pair. Whoops. Okay. So let's see. Here's with the 2. Now let's consider with the 13. So let's see. Multiplication. Well, 12 times 13. We did that up here. That was 156. And then 12 divided by 13 is some weird decimal that I really don't think is going to be useful. And then the 11. So 12 and 11 would be 23. If I could just get another 1. But my other 2 numbers in that case would be 2 and 13, and I don't see how to extract a 1 from them. 12 minus 11 would be 1. Let's see. 12 times 11 would be 132. And again, I don't think the division is going to be helpful. So if we had 12, 11, 12, 11, we could just get it by doing that. But that is not our assigned problem here. Okay, so we know the 12 has to be paired with something. So somewhere in these options, we should have a route to 24. So now let's look within each of these at what the options would be to do with the other 2 numbers. So for 12 and 2, the other 2 numbers would be 13 and 11. So 13 plus 11 would be 24. If I could get a 0, that would be great, but that's not on my menu. Okay, 13 minus 11 would be 2. If I had a 22, but I don't. Let's see. 13 times 11 would be 143. I don't see that helping. And 13 divided by 11 would be some weird decimals. That's not going to work. Now, on the other hand, if I pair the 12 with the 13, my other 2 numbers are 2 and 11. So let's see. 2 plus 11 would be 13. So I can get back to 12, but I don't see how to get back to 24. 11 minus 2 would be 9. And then 11 times 2 would be 22. So I could get to 23 by adding together this 1 and this 22. But I don't want 23, I want 24. Okay, now on the other hand, there's that 11 there. So let's see. So if 12 and 11 are paired, then 2 and 13 are my other two. So how can I pair those? Well, let's see. So I could say 13 plus 2 is 15. 13 minus 2 is 11. And 13 times 2 is 26. If I could subtract a 2 from that, but I don't have a 2 over here. What if I could reduce this 13 by 1? There we go. I think I'm onto something now. Okay, so 13, but I want to do 13 minus 1 times 2 equals 26. Okay, but where am I going to get that minus 1 from? Well, I see I can get a positive 1 here. So if I do 13 minus 12 minus 11 times 2, I think that's not 26. Whoops, 24. Whoops. Let's see, 13, 12 times 2, 24. Okay. Now let's see, 12 minus 11 is 1. 13 minus 1 is 12. 12 times 2 is 24. Okay, I think we've got this. I'm just going to click this into this other site and have it check. So let's see. Let's see, it doesn't have parentheses, so how do I need to do this? So I need, let's see, 11 minus 12, that's going to give me negative 1. And then plus 13, that's going to give me 12. Well, let's just see how this thing, let's see, 11 minus 12. Okay, that gives me a negative 1. Okay, negative 1 plus 13 is 12. 12 times 2 is 24. Okay. Okay, and there we go. We've finished the puzzle. So the next question you might want to ask is, how did the computer know that these numbers would work? And I'll be honest, I haven't figured that part out yet. But I'm sure there's a way to figure it out. Okay, so let's circle back to this alternate number universe. So let's see, we already said that 2 times 3 is 6. Well, I'm going to tell you that 3 times 2 is also 6, and that shouldn't be surprised because I mentioned that that our idea of multiplication in this universe is similar to our idea of multiplication in the normal universe. Like it kind of follows along with repeated addition, except when things get weird. So we know that 2 plus 5 is 3 normally, and in fact 2 plus 3 is 5. Well, getting things backwards. And alternate universes can be a little tricky to deal with. So we know 2 plus 3 is 5 normally. Well, we also know that 3 plus 2 is 5. Oh, whoops, I did that one already. Let's see. We already have that 1 plus 3 is 4. Well, now I'll tell you also that that 3 plus 1 is 4. But just coming back to this, so it seems to be the case that we're going up by 3s. So does that mean that 6 plus 3 is 2? It turns out that that's true. 6 plus 3 is 2. Ugh, that seems so weird, right? Okay, so I really would like to see some guesses about what's going on in this alternate universe. But for the moment, I need to switch over to Algebra 1.5. Okay, so this is our Algebra 1.5 lesson for today, and this is going to follow along with some of what we introduced last time, which was evaluating expressions. Well, now we have goals in how we want those expressions to evaluate. So the first problem that I have handy is the equation 6x minus 5x equals 0. Now this means we have a goal here. Algebra books will often just say, or not even say, expecting you to just take it as implied, solve the equation. Well, what exactly does that mean to solve an equation anyway? You know, does it have a problem? Is its faucet leaking? You know, does it have some kind of problem like that? Well, it turns out what we really want to know is a particular value of x. And sometimes it might even say solve for x. Quite often when there's only one variable in there, it'll expect you to take it as implied that it means solve for that variable. When there are two variables, it's got to tell you which one because either could be equally valid. Okay, so here's what this is actually saying though. We want to know that there's that the value of x is some number based on the goal given in this equation. So we want to know that x value so that 6x minus 5x evaluates to 0. So we can start by making a bit of a chart. So we can try out different values for x and see what happens. So let's take a look. So first of all, let's try out saying that x equals 1. Why? Because it makes our calculations really easy, and if we're just trying things anyway, we may as well try something that's going to be easy. So that tells me what I'm going to do is copy this over with spaces opened up for our value that we're plugging in, and then I'm going to go back and plug it in, and I'm even using a different color. Okay, so what we're looking at is 6 times 1 minus 5 times 1. Well, 6 times 1 is just 6, and I'm using the order of operations. I'm not writing it down because this one is pretty easy, but if I had a lot of steps to do, it could be a good idea to write it down. So 6 minus 5 is 1. That's interesting. Let's try another number. So what if we try 5? So this time, instead of plugging in a 1, we would plug in a 5 everywhere there had been an x. Then we'd be doing, okay, 6 times 5 is 30. 5 times 5 is 25. 30 minus 25 equals 5. So it seems like there's a pattern going on here, and it seems like we're getting back the same number we started with. Well, what's up with that? So it turns out this expression here, 6x minus 5x, can be simplified. So let's suppose for a minute that that is x. Okay. Okay, so that would be 6x, right? We've got 6 x's lined up. So here we've got 6x. And then if we get rid of 5 of them, so 6x minus 5x. Well, what's left? Just an x. Okay, so now we can make our simplifying process much easier because we know if we plug in 7, we're going to get back a 7. If you don't believe me, feel free to plug it in and simplify. It's always okay to check. So we'd have, let's see, 6 times 7, well, that's 42, minus 35. Seven. Okay, but we had a goal here. We want to know x so that that comes out to 0. Well, the only way we're going to get 0 out of this thing is by plugging 0 in. So we need x to equal 0. Now, your algebra teacher may not want you to do a bunch of guess and check because a lot of the time it ends up being inefficient if the answer is something like 17 296ths that you would just never guess. So the official method for solving this problem would be to say, okay, well, I know that 6x minus 5x is just going to be x, so x needs to equal 0. In this next problem, I have that 17 equals y plus 3 plus 6y. Okay, so again, our goal is to solve that equation. And what does that mean we want to know? So I hope you took a minute and thought that over. So if we want to know the solution to this equation, that means we want to know that y equals some particular number so that y plus 3 plus 6y comes out to 17. Well, just like we were able to simplify the other expression, I see a lot of terms in this right-hand side, so let's take a look and see if we can simplify that. So now I'm going to say that this is y, and by the way, I'm not saying by that that y equals 3, I'm just drawing a rectangle and I'm using the grid to help me with it. So I need a bunch of y's. Let's see what happens. Okay, so here's our y. And then we're going to have some units. So there's our 3. Okay, so we need another 6y. Okay, well, it seems to me there's a much more efficient way to write this, because what if we just put all the y's together? So I'm not changing the value. I'm not taking anything out of this side of the equation. I'm just saying, okay, what if we move the pieces around a little bit? And so then we could have 3 plus 7y. So what we've done here is we've combined like terms. So combining like terms is a thing we often do in algebra because it makes a new expression that's tidier and easier to work with. So out of this equation, we can combine these two terms and get 7y. Okay, so we're looking for a number that we can multiply by 7 and then have 3 added to it and get 17. Well, that seems tricky again, so let's try some things out. Some y's and some calculated 3 plus 7y's to see what's going on here. So again, we could try 1 because it's easy to work with. So 3 plus 7 times that. Okay, so 7 times 1 would be 7. Bring along the 3. Well, that would be 10. That didn't come out to 17 like we wanted it to, so we need to try again. So let's try 2. So let's try plugging in that 2 instead and see what happens. So then we'd have 14, and then 3 plus 14 gives us 17, just like we wanted it to. So that tells me that the y value we need is 2. But again, we don't want to be overly dependent on guess and check. So how could we find this out without guessing and checking? Because what if it were something outlandish? In fact, let's do a harder related problem. So what if instead of 17 over here, we would have started with 12. So 1 is too little, 2 is too much. You might be tempted to try 1.5. So let's see, 3 plus 7 times 1.5. Let's see, that would be 7, and then half of 7, so 10.5. So we'd have 3 plus 10.5 would be 13.5. That's still too much. Okay, so we could chase this down a lot of steps of guess and check, and I'm not going to stop you from doing the problem this way, but I'm going to say, hey, there's an easier way. So first of all, what I recommend you do is combine your like terms, just like we did in the one before. So we'd be saying that 3 and 7y make 12. So then a way you can deal with this is to perform some algebraic steps on the equation to solve it out. So we know that the right-hand side of the equation is this 3 plus 7y. And we know that the left-hand side of the equation is just 12. And we know that these things are the same as each other. That's important. So this, whoops, I should draw that lower down. So this and this, in spite of how much bigger this looks, balance. Okay, so what comes to mind is, well, what's balancing with what? Well, one thing I can pretty safely infer is that these are balancing against these. So what if I take them off? Okay, so then we still have to ask, well, still though, what is balancing against what? So we've got 9 over here and 7y over there. So we could try to say, okay, well, let's rearrange these so that we can see what's balancing against what. So one thing we might attempt to do is say, okay, well, and I'm going to line these up this way so that I can put them in rows. I'm just going to see if I can do the whole thing at once. Okay, it'll go. I need more room, so I'll do that. Okay, so what's going on here? Well, we've got these y's that we can put in rows, a row for each y, and I need just a little more room. Okay, that should do. And what's each of these balancing against? Well, we can spread these out and say, okay, that's balancing 1, and that's balancing 1, and that's balancing 1, and so on. Whoops, I put those too far over. Okay, that's better. Okay, so each y is balancing a little more than 1 because what I'm seeing is we still have these left over. So we need to take these two individual units and split them out in equal parts. So we have two wholes being split in 7 directions. Okay, so if we have those two wholes being split in 7 directions, then each of those directions will get 2/7 of a piece. But then we can divide this up. So that y is balancing that piece and 2/7. That y is balancing that piece and 2/7, and so on. And so we can see from this that each y balances against 1 and 2/7. Well, if they're balancing, they must be equal. So that tells me that y equals 1 and 2/7. Okay, now it seems inefficient to have to draw diagrams for all of this. So for shorthand, we would often say, okay, well, the first thing we did was subtract 3 on both sides. That's this step right here. That was very straightforward. So then we were saying, okay, that 9 is the same as 7y. And I could use a little more space, so I'm going to move this over here. Okay, so then what happened? Well, then we divided each side into 7 groups. Why 7? Because we had 7 y's. And so that tells us that 9/7 is the value of y. But now you're saying, hey, wait, what's going on here? We're getting 9/7 here, 1 and 2/7 there. Well, so first of all, for algebra, usually this answer right here is good enough. Now, sometimes for an application problem, you might need something in a little bit different form. So you might say, okay, let's simplify that. So let's say, let's take that 9 and divide it by 7. We get 1, multiply with a remainder 2. So what we have there is 1 and 2/7, just like we got before. Sometimes you might need a decimal. I'll be honest, decimals are not the preferred option in most algebraic problems, but for some applications like money, you need them. So if you need that for this, what you would do is say, okay, grab a calculator because that's the easiest way, and we like to do things the easiest way. So let's see. 9 divided by 7 is approximately 1.29. And again, that's an approximation. That's why I use the approximation sign. So for some applications, you would need this, like if you were saying, okay, well, we need $1.29. But usually we would prefer this version, and then this version is okay. For some applications, though, this might be useful. For some, this might be useful. But if all they give you is an equation, then just the 9/7, the improper fraction version, is quite all right. By the way, when we divided 9 by 7, we got a remainder of 2. In problems up here that we would think come out to 9, like 5 plus 4, we're getting 2. 6 plus 3, we're getting 2. Why is that happening? Oh, here's another one. 3 times 3, we're getting a 2. Okay, what's going on here? Okay. So I want to jump a little bit, though, from alternate number universes and talk a little bit about a particular exponential function. And then you're like, Avrila, wait, what? That's not an exponential function. That's a crocheted simulated coral. Well, okay, or maybe you didn't get all those details, but it sure looks like a head of coral, doesn't it? Well, it turns out that there's an exponential function that makes this thing. So if you look really close, I'm going to see if I can get this close enough to the webcam that you can see. Okay, it's getting blurry. Okay, that's not so bad. If you look really close, there are a couple of different things that happen in crocheting this. So where I'd like to direct your attention is right here. See in the blue ones how that spot looks a little thicker than its neighbor here or over here? And okay, I'm mirror imaged in this, so this is really hard to see what I'm doing. Okay, so what we have here is a regular one, a thick one, a regular one, a regular one, and then again, it's starting to be hard to see because we're going into a lighter color, but here's another thick one. Why are they thicker? Well, it turns out those are 2 stitches in one. So how does that make an exponential function? Well, here's the cool thing about it. So, and I'm going to grid this out using diagram notation. So here is the diagram symbol in crochet for a single crochet stitch. And let's say it's into, let's not worry about what it's into for a minute. So let's say we have several of those. Okay, so let's say we're going along. Okay, 1, 1, 2 to increase. Okay, so what we have here is that 3 becomes 4. 1 single crochet, 2 single crochet, 2 to increase. 1, 2, 2 to increase. Okay, so you see how this is getting crowded? Well, what really would happen is it would spread out further because the yarn's not going to suddenly be narrower for just those 2 stitches. So we get increasing size of each row, or in this case, each round. So then we would come back and go again, say 1, 2, 3 increase because 3 becomes 4. 1, 2, increase. 1, 2, increase. 1, 2, increase. Okay, so we started with 9 stitches, then 3 became 4, so we had 12 stitches. Then let's see, each 3 became 4, so 4 3s became 4 4s, So we had 16 stitches. So what we have here is an example of an exponential function. But what's it going up by? Well, if 3 becomes 4, then it's going up by a factor of 4/3. So each row's number of stitches, I'm just going to say n for number. So the number of stitches on row, say A, times 4/3 will give us the number of stitches on the next row. Let's say row A plus 1. So how many stitches does that get to? Well, that's an interesting thing. Exponential functions have this general shape. They increase rapidly, and they increase at an increasing rate. So when you have something increasing at an increasing rate, well then, oh, whoops, my mistake. I forgot to switch back over to that screen. Okay, so let me talk you through this quickly. So I jotted down, whoops. So I jotted down how 3 stitches becomes 4 stitches by doing a stitch, and then a stitch, and then an increase with 2 stitches in it each time. So I started with 9 stitches, 3 became 4, I got 12, then each 3 became 4 again, and I got 16. So since 3 becomes 4, we're multiplying by 4/3 each time we go up, so 9 times 4/3, well the 3's cancel, so that gives us 12, just like we got there. 12 times 4/3, the 3 cancels, leaves a 4. 4 times 4 is 16. There we go, just like we expected it to. And in general, that follows the pattern of a formula or a graph that is increasing at an increasing rate. So this function that shows us the number of rows is an exponential function. Well, why is it called exponential? We didn't put an exponent anywhere in that. Well, it turns out that if you start from a particular number and keep repeating this, like say we have 9, and then 9 times 4/3, and then 9 times 4/3 to get that row, and then times 4/3 to get the row after, and so on. Well, another tidier way we could write this is 9 times 4/3 to whatever power we needed. So that's where exponential comes in as the name of this function, and we see that each row is getting longer and at an increasing rate. In this case, they're rounds, not rows. But one result we can see from this is that that as it continues increasing, each round is just longer and longer wildly until it can't just go around. It has to kind of go back and forth to kind of make up for its length by zigzagging around more. And as a result of that, you get this neat curled look that reminds you of a coral. Not a coincidence. This is representative of things to do with the way corals grow. So this is something you can try out and explore some math with if you are into yarn crafts, or if you would like to get into yarn crafts. I'll be happy to post some more information about these too. You can also do some investigations about like non-flat geometry by folding these and seeing what a line looks like. Okay, so you can see that I've got this folded flat, but it's not always staying out straight like this. It's able to curve back in on itself. And what if we took a yarn needle and a contrasting color of yarn and sewed some shapes onto this? Well, what would what would those shapes look like? So there's a lot you can explore in this. It's definitely a fun thing to do if you've got some time. Okay, so that was a preview of something that's coming way ahead as part of Algebra 1.5, because we will get to exponential functions in there, but again, later on. Okay, so I want to jump back to this alternate number universe before we wrap this up. So in this alternate number universe, I pointed out that there was some connection, and I'm going to make an extra page to move some things onto here. And I'm going to drag our work from the other problem onto there. Probably should have done that in the first place. I'll try and remember that for next time. This, by the way, is a program called Write from Stylus Labs. It's meant for on an Android tablet, but it also works on a Linux desktop computer if you have an external tablet for it. And I find it really useful for writing out my work on math problems. And whoops, that got miswrote somehow. Okay. So does anybody have a last guess before I go on and give spoilers about what this alternate number universe is? Well, I'm going to use this one to help us out with this. So what's today? Wednesday? Whiteboard Wednesday? Okay, well, let's see. Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. Okay. 1, 2, 3, 4, 5, 6, 7. All right, so today is Wednesday. In 5 days, 1, 2, 3, 4, 5, it will be Monday. So this alternate number universe, where we actually spend time anytime we look at a calendar or do something else with days of the week, this alternate number universe loops back to the beginning after 7. Okay, so now we can fill in the rest of our addition table. So let's see, 1 and 1 makes 2. Well, that's on there. Let's see. 2 days after Sunday would be Tuesday. And we can just say, okay, the usual patterns will work until we get up to 7. And then let's see, 6 days after Monday. 1, 2, 3, 4, 5, 6. That'll be Sunday. 5 days after Tuesday, same thing. And then another day further is still another day further, even if it goes around the end of a week. So we have an addition table. Now what's missing? Well, Saturday. So let's see, 7 days from Sunday. Well, that'll be another Sunday. So 1. 7 days from Monday. 7 days from Tuesday is Tuesday. 7 from Wednesday is Wednesday. 7 days from Thursday is Thursday. 7 days from Friday is Friday. And 7 days from Saturday is Saturday. Similarly, Saturday and 1 day is Sunday. Saturday and 2 is Monday. Saturday and 3 is Tuesday. Saturday and 4 is Wednesday. Saturday and 5 is Thursday. Saturday and 6 is Friday. Okay, so we see some familiar patterns in this addition table, even though it's from an alternate universe. So we see the same numbers on the diagonals, even after the great weirdness here, where it wraps around to 1 and 2 again. Let's see. We also see that it reflects nicely, so addition is commutative in this alternate number universe. Now here's something I notice. Usually we're used to saying, okay, if we add something and get the same thing back, what we added must have been 0. Well, here we're getting that property from 7. So that is a particular property of this alternate number universe. And in fact, that gives us another way we can name these numbers. So what we could say is, what we really have here is 1, 2, 3, 4, 5, 6, and something that acts like a 0. So we can rewrite our multiplication table with that in mind. And I'm just going to also delete this notation about which is first, because now we know that doesn't matter. But I am going to put in that we are turning it around to a 0. And I'm going to take off the 7s because that is customary in an alternate number universe addition table, that if there's a 0, you write it as the 0. So what that tells me is that seven is equivalent to 0. And what this number universe is called is the integers mod 7. You may also see it written this way as Z7, like that. Okay, so I'm going to cut off this feed pretty quickly, fairly soon now, but I'd like to leave you with some problems that you can work on. So let's see. What I'm going to leave you with is, how does multiplication work? In this integers mod 7 universe. Let's see. And so we know that it's consistent with repeated addition, but what else? Let's see. And then the other question I'm going to leave you all with is, what other alternate number universes might there be and as a sub-question of that, how could we explore them? So you'll notice that these last two questions are really open-ended. there are whole, you know, whoops, I forgot to switch that back again. Okay, so how much did we miss from that? Okay, so basically what I had pointed out was that we've got some nice patterns in this alternate number universe, and it's called, again, the integers mod 7, often written with this Z7 abbreviation here. Addition seems to work the usual way until we get to this point right here, where it does that weird wraparound. Oh, I just saw one more thing I should fix. So if we're using this 0 through 6 representation of it, those 7s would actually be the zeros that represent Saturday. Okay, let's see. So we've got just this. It's just mathematically customary to label the numbers this way. Let's see, what else? So then I was leaving you all with some questions. So one of my questions is, how does multiplication work in the integers mod 7? What other alternate number universes might there be, and how could we explore them? So keep your eye out for anything that you think might be an alternate number universe, and anything that might be a usual, an interesting pattern in it. And oh, I'll give you one more question on this. So we said that 7 is the same as 0 mod 7, and we said that 9 is the same as 2 mod 7. So I'm going to say, how could we calculate say some number equals its equivalency class in mod 7. Whoops, not mod n, mod 7. N's on the brain. Okay, wow. So that would be for any value of n. Okay, so if there's anything up here that doesn't make sense, please let me know. I'm really sorry I forgot to switch back. And other than that, for the moment, I'm going to say it's been a really fun Whiteboard Wednesday. I'll announce on the blog when I'm going to do this again. I need to check my schedule and see if next week or the following week would be a better schedule for it. But for now, I'm going to say I am Avrila at Math with Avrila. Calc you later.